Hi, it's a guy Holumde, and today we are gonna be solving another one of the most commonly asked tech interview question by top tech companies including Google, Amazon, Netflix, Meta, Microsoft, Apple, and other top tech companies. The title of the problem is Find the target in a rotated sorted array. A rotated sorted array is an array of numbers sorted in ascending order in which a portion of the array is moved from the beginning to the end. For example now, a possible rotation of this particular array 1, 2, 3, 4, 5 is 3, 4, 5, 1, 2. So it's a situation whereby a portion of the array is moved from the beginning to the end. So where the first two numbers here, we see that the first two numbers in this case 1 and 2 is moved to the end. So I moved to the end of the array, and this 3, 4, 5, which is the last three numbers, are now at the front in the corresponding array. So that's what it takes to rotate a particular array. So now the problem statement says that given a rotated sorted array of unique numbers, return the index of a target value. If the target value is not present, return -1. So we will be given a rotated sorted array of unique numbers, and we will be asked to return the index of the target value. Look at this now. We see that this is a rotated sorted array because the first 1 to 7 is shifted to the end, while the last 8 to 9, which are the last two elements of the array, are now shifted to the front. So it is rotated. We are now asked to find the target 1, and then the output returns 2. So you will note that the output is not actually the output of the sorted array. So the problem is not asking us to sort the array and to return the output. It's actually asking us to return the index of the particular target in this same rotated array, in this same rotated sorted array. So how are we gonna solve this problem? Let's see. A naive solution to solving this problem is to iterate through the array norms until we find the target. So we can keep iterating until we find the particular target, then we can return the index of the target. But this is gonna take a linear time to solve, and we are not put into consideration that we are given a rotated sorted array, that the array is sorted just before it is rotated. So let us take into consideration of the fact that we are going to be provided with a rotated sorted array, and let us see how we can solve this problem using the binary search technique. So as a first step in solving the problem using a binary search approach, if you look at our previous video, you will know that the first step is to define the search space. So, and if we look at this, to define the search space for this binary search is gonna encompass the whole array, because the array could be in any position along the target could be in any position along this array. So the search space will encompass the entire array, meaning that right from the beginning here to the end of the array. Now let's figure out how to narrow our search space, whether to the right or to the left. This is a very interesting challenge, considering the fact that our array is not totally sorted, it is actually rotated. So now we are gonna explain how we are gonna narrow the array by considering this example. We are gonna set our left and right pointer at the boundary of the array. So, and then we are going to use that left and right pointer to determine the midpoints, so which appear here. So for a sorted array, it is quite straightforward to determine, right at this point, based on the value at the midpoint and the target value, you can decide whether to narrow to the left or to the right. But considering the fact that we are dealing with a rotated sorted array, this won't be as straightforward as that. Now, to determine which direction to narrow our search space to, we are going to be visualizing each number in the array as a tree, something like this. We are going to be visualizing it into this bar. You understand? So look at this now. That's the first element in the array has height of 8. So the bar here is 8. The following one is 9, 1, 2, 3, 4, 5. And also we'll be considering the left and the right subarray, these two subarray, the left subarray which encompasses the middle value right here, the middle value right here now, and so left will be considering these two array from the left pointer to the middle value and also the middle value to the right pointer. So why we are including the middle value is because the middle value is gonna be important, is gonna be useful in deciding where to narrow our search space to. Now this is what I mean. Right here we see that for the left subarray, so don't forget the left subarray is the one that has left to mid, and then the right subarray is the one that have mid to right. You can observe that when we merge the left subarray and the right subarray together, it form the whole array. So now looking at the right subarray now, that is from the mid to right, we see that it is sorted. If we look at this visualization right here, this is the mid value 3 followed by 4, 5, 6, 7. It is sorted. Now since it is sorted, we know the smallest and the largest value in the range for this particular right subarray. We know that the smallest value is 3 while the largest value is 7. This means that we can check if the target is in this particular subarray, I mean the right subarray now, since the right subarray is sorted 3 to 7. So we can know if the target is there by trying to check if the target is within the range of 3 and 7. So, and if we look back into the question, the target here is 1. So 1 is actually not in the range of 3 and 7. Why? Because 1 is less than 3 and 1 is less than 7. So it is not even in the range of 3 and 7. Therefore, this means that 1 is not in the right subarray. Definitely, we need to check it's out of the right subarray. We need to consider the left subarray now. Consequently, we see that we need to narrow our search space to the left. Why? Because the right submatrix won't contain the target, because the target is 1 and the range of the right submatrix is 3 to 7, which does not include 1. So, and we know that 3 to 7, the right submatrix is sorted from 3 to 7, so there's no way it's going to include 1. So we have to narrow our search space toward the left. And that means we can narrow it by moving our right, by shifting the right pointer to mid minus 1. So to this position 2. Just like we can see it in this visual. You might be like, why do you have to set it to mid minus 1? Why not just narrow it down to mid, since it is only mid that we consider? Fine. You see that mid itself does not equal the target we are looking for. So right, mid is 3, it is not 1. So there's no need of encompassing mid inside the space tree any longer. So we just have to shift our right to mid minus 1. So, and doing that now, our mid position in the next iteration, in the binary search, is gonna fall at 9. Why? Because our right pointer has been shifted from the last index to mid minus 1, and right now our new mid will be the average, which is gonna fall right here. So it's the normal average left plus right divided by 2. You might be wondering that why do we not use left plus right divided by 2 plus 1? Well, the additional plus 1 is used in case of when we are finding the upper bound. So, and since we are not finding the upper bound, there's no need to use mid equals to left plus right divided by 2 plus 1. Just left plus right divided by 2 is fine, since we are just finding a single occurrence of the target, not upper bound or any other thing. So placing the mid right here now, we are gonna look again in the mid. The mid is pointing at 9. Fine. Okay, if we look again at the visualization of this little space tree that we have narrowed down to, which is 8, 9, 1 and 2. That's our new space tree now. 8, 9, 1 and 2. So this is it here in the visualization. If we look at it, we see that 8 and 9 are sorted. So, and now, fine. If we look at it now, we'll be like, fine, 8 and 9 are sorted. Now, is the target between 8 and 9? The target is 1, like we have in the problem statement. And so 1 is not between 8 and 9, meaning that 1 is far less than 8 and far less than 9. So it is not in this range of the left subarray. So what we do is that it's definitely gonna be in the right subarray. Why? Because it's not in the range of the left subarray. So what we do is we shift our left pointer to mid plus 1. Why? Because the mid pointer falls at 9, and now 9 itself is not equal to target, so there's no reason why we need to keep the 9. We can just shift our left pointer away from 8 right to 1 at this point 1, so at the same time ignoring 9 itself. So, and that's what we did there. Why we shifted it beyond mid, why we shifted it to mid plus 1 is because 9 itself is not equal to target, so there's no need of keeping it in the space, in the search space. So doing this now, we are left with these two elements in our search space, and when we find the mid, it's gonna fall to the left, and falling to the left now, we see that the mid is actually pointing at 1, which is our target that we are finding. The mid is now pointing at it, so we are gonna return the index of this mid because it is pointing at 1, which is 2, because 2 is the index of this 1. So that actually open our eyes to the fact that right before we narrow to the left or to the right, we first of all check at each position of mid that is mid equals to the target we are looking for. If it is, just return the position. If it is not, then you can follow on with the narrow, with narrowing, checking if the left is sorted or if the right subarray is sorted, and going for the one that's sorted. Try to check if the target can be in that range of the sorted array. If it is not, you shift it to the left, you narrow to the left or narrow to the right. But before that, you first check if mid is pointing at the target. Just like in this case, mid is pointing at the target, so there's no need of narrowing any longer. Since we now have the index, we can access the index of that target, we just return it. So that's how the logic actually goes. So I'm gonna summarize it now for a clear understanding. Okay, right from our discussion above, we see that there's a specific strategy that we use, and it is the fact that right from our mid position, we are gonna be able to divide the array into 2 right from a particular mid position. So consider this mid position right here. We will divide the array into this left subarray and the right subarray. So the left subarray is gonna be the very first element to the left, the very first element in the array to the mid position, while the right subarray is going to be the mid position right to the very last element in the array. Well, we cannot say that last element in the array or first element in the array, because we actually define a search space. So depending on how we are narrowing down the search space, that's gonna tell us the first element and the last element. Look at in this case now, we already narrowed away all these 3 upward, 3 4 5 that is underlined like this, and this one also that is overlined like this. So meaning that our search space is gonna be left to right. So if I'm trying to talk about the first element, the element that the left pointer is pointing to. If I'm talking about the right element, the element that the right pointer is pointing to, because we do narrow down the search space. So depending on that position, depending on the mid pointer, we divide our array into 2, left to mid and right to mid, and any one out of these 2 that is sorted is gonna define where our target is going to be moving. Why? Because I told you, if left to mid, if this particular subarray, the left subarray, if it is sorted, what we do is that we try to check if our target could exist within that range. You understand? So if it is sorted, we check. Look at this situation now. 8 and 9 is sorted. Then we try to check our target 1. Can it fall between 8 and 9? Why? Because 8 is to the very left, 9 is to the very right of our left subarray. Understand? And so is either our array falls right under 8 and 9. If it does not, then our left subarray is out of it. We are just going to consider the right subarray. So right from the mid position, we are going to divide our array into 2 subarray, the left and the right subarray, and depending on whichever is sorted, we are going to check if the target is in that sorted array. If it is, then fine, we know that we are going to narrow it to that particular toward that direction. If it is not, we are going to narrow it to the next direction. So, and we are going to be considering 2 cases now. So just to explain what I just said now, the first case is that the left subarray is sorted. Don't forget, we have 2 subarray from the midpoint, left and the right. So the left might be sorted. If the left is sorted, the right might also be sorted. It doesn't matter. But if the left is sorted now, what we want to do is that we want to check if the targets fall in the range of this left subarray. If we do fall, we narrow the search space toward the left. Otherwise, meaning that if it does not fall in the range, consider we are looking for 1 now, and then the range is 8 and 9. There's no way 1 wants to be found between 8 and 9 and it's gonna be sorted. No, we can't have a sorted array of 8 and 9 and find the 1 inside of it. So in situation like that, we're gonna narrow our search space towards the right. So let's consider that case now, whereby the left subarray is sorted. So look at here now. Look at this particular example given here, 3, 4, 5, 6, 7. You see that the left subarray is sorted now. Why? Because we are gonna, if we place our left at this very first element and we place our right at this very last element, our mid pointer is gonna fall at this 6. So, and when we compare the left subarray and the right subarray, don't forget that the fact that the mid pointer falls here, we are going to be able to divide our array into 2. One will be from 3 to 6, the other will be from 6 to 2. Now, which one of them is sorted? We say that this left subarray is sorted. Fine. Our target now that we are looking for, is it in the left subarray or in the right subarray? I mean, since our left subarray is sorted, definitely is actually enough to divine if we are going to be narrowing to the left or narrowing to the right. No need of considering the right subarray. So if the left subarray is target, just like in this code snippet here, if norms of left is less than equals to target, which is less than equals to norms of mid. So at this point, we are quite sure that our left subarray is target is sorted. Now we want to check if the target falls in that range of the left subarray. So if we do, what we are going to do is that we're going to shift our right pointer right from the last to mid -1. Why? Because first of all, the left subarray is sorted and the target now exists within that range. Definitely it is to the left. We're going to be narrowing to the left. But in a situation whereby the left subarray is sorted, fine, but the target does not exist in the range, what we are going to be doing is that we'll be shifting to the right. Why? Because there's no way we're going to find our target inside that left subarray, because it is sorted and it does not encapsulate the target we are looking for. Imagine 3 to 6 and we are finding 7. So there's no way 7 to be between the two walls, between the two boundaries, 3 and 6. So that's what we're trying to say. And in a situation like that, we're going to narrow our search space to the right by shifting left to mid -1. So that's the first case. Now the second case is a situation whereby the right subarray is sorted. So you see, once the left subarray is sorted, you just have to perform this operation, while once the right subarray is sorted, we perform this the same set of operation, but just some little difference. And what we are going to be doing is that, similarly, fine, the right subarray is sorted. We want to check if in that sorted subarray that is to the right, if the target really exists in between them. And how we can do that is trying to check from the mid value. Don't forget that the mid is what divide the left subarray from the right subarray. So we want to check if mid value is less than the target. Fine, we know that the mid value is not equal to the target. Why? Because that's the very first thing we check. If the mid value is the target, if it is, there's no need of dividing or narrowing, just return the index. You already get the answer. But in a situation where the mid value is not equal, then we can divide into the left subarray and to the right subarray. And what we want to do is that if the right subarray is sorted, we want to check if the mid value, which is 6 in this case, if it's less than the target and the target is less than the norms of right. Don't forget that this particular array, the right subarray is sorted. Definitely the value at the middle is going to be less than the value at the end. So I'm giving it as an illustration, so it might not look like that right here. So imagine now if the mid position fall at here, so we can say that it might look like that. So I'm just giving it as an illustration now, that if the right subarray is sorted now, we want to check if the target lies between the mid value and the end position, that is the right pointer. So if it do exist, then we can navigate the left or navigate or narrow the search space to the right by shifting left to mid plus 1, because we are now assured that we are gonna find the target in the right subarray. Why? Because it is sorted and it encompasses the target. So but in a situation whereby it is not sorted, what we wanna do is that in a situation whereby it is sorted but it does not encompass it, that ring does not contain the target, we want to shift our right pointer to mid minus 1, just like in this case. So the first set of things, define your space tree or your space your search space. After defining it by setting the left and the right pointer, then you choose a mid position. By dividing the left the sum of left and right divided by 2, you are able to choose a mid position. So from that mid position, you will evaluate if the left subarray is if it is sorted. And now you can evaluate it is by taking the left pointer, looking at the array from left pointer to mid, if it is sorted, or right from the mid to the right pointer. Anyone that is sorted between them, you then try to check if it contains the target. It will definitely start with a value and end with a value, and because it is sorted, that value will be the two extreme value. That is, the value to the left will be the highest, while the middle value is going to be the value to the left is going to be the lowest, while the mid value is going to be the highest in that left subarray. So, and then depending on that, you are gonna check if it can contain the target. If the range is between 3 and 6 and what you are finding is 1 or what you are finding is 7, then it cannot encompass it. So in a situation like that, you are gonna shift your you are gonna narrow toward the right, because the left is sorted but it does not contain the target. But in a situation whereby it is sorted and it contains the target, fine, you will narrow to the left. So same thing, exactly same thing applied to right pointer, because if it is sorted, fine, you try to check if it encompasses the target. If it does not, narrow to the left. If it does, narrow to the right. And that's how we can solve this problem. We're going to be going to the code implementation now. It's going to be interesting, so kindly follow along. Alright, let's move into the code implementation now. We'll be defining the function find target in a rotated sorted array, and then we'll be collecting the nums, so which is a list of integers that contain our rotated sorted array, and also a target k, which is also an integer that want to find its index. So we'll be returning that particular index, which is also an integer. So now let's define our boundaries. The first thing in a binary search algorithm is to define the boundary. So for the search space, we're going to define it as left and right, so to be 0 and len of nums minus 1. So while left is less than right, why we place it as left is less than right is because we want to loop out at the point whereby left becomes equals to right. So while left is still less than right, keep on iterating on. So why? Because at the point whereby left become equals to right, mid is gonna be at the same position. So left, right, and mid will continue to be at the same position. So it can lead to an infinite loop. So we have to really cut when they become at the same position instead of continuing. So the loop is gonna be valid while left is still less than right. So once they become equal, we're gonna be cutting out. So let's define our mid position now to be left plus right, so divided by 2. So that's simply our mid. So if nums of mid, so you might be like, why are we using left plus right divided by 2? That's actually the standard way to find the middle position, adding and dividing, so that it can give us the middle of the array. So but in a situation where we are finding the upper bound, so that used to cause us to put +1 there if we are finding the upper bound. So you can look at my previous video if you've not watched about the upper bound. So upper bound is when you have a list. Probably you are looking for the first and the last occurrence of 4. Here in this question we have to find the index of the target 4. So target 4 appears once, so every number appears once in this particular array. But in a situation whereby the target could appear more than 4 times or more than once, and we want to find the very last time that it occurred, that's what we call an upper bound. So, and that's when we'll be having to put +1 at the back to avoid an infinite loop. But in this situation we can just follow the normal standard. So if norms of mid is in or if is equals to the target that we're looking for, what we want to do is that I want to return the mid itself. Don't forget that's what the question asks us to return the index. So if is equals to k, which is the target we are looking for. So but in a situation whereby it's not equals to k, elif then we want to check. We are gonna divide our array into 2 based on this mid value, so the left subarray and the right subarray. So and how we're gonna do it is that elif norms of left, elif is less than or equals to the k we are looking for. Okay, elif is less than or equals to norms of mid. So what we are doing this is that I want to check if the left subarray is sorted, and how to do that is to check if the very first element is less than or equals to this particular element at the middle value. So if the very first element, or not very first element really, not necessarily the very first element, but the element that is represented at the leftmost of this search space, if it is less than or equals to this middle value, then we can be assured that it is sorted. And what we want to search again is that, okay, if norms of left is less than or equals to the target k, which is less than norms of mid. This way I want to check, fine, it is sorted for it to reach this condition, for it to come into this if condition, this particular one here, and to settle down to check this one. That means it is sorted. And now the next thing I want to check again is if the targets fall within that range of the sorted array, the left subarray. Now if it fall in the range, meaning that if the very first element, of course it is less than the middle element. Now if it is also less than or equals to k, which is now, and k should be less than the norms of mid, meaning that if it's either at the left element or in between the left element to the middle element, then it is, we know that we can find it there. And what I want to do at that situation is I want to navigate to the left. Why? Because the target exists between the left and the middle pointer. So our right pointer should be moved to middle -1 so that it can narrow the search space. Otherwise, if it is not there, we want to set our left to mid +1. It means that fine, it is sorted, but the target is never in between, it's never in that range, so it's not even close to those places. And we want to set our left pointer to mid +1 so that it can even override that whole left subarray. It will narrow it down to the right by setting left to mid +1. So but in a situation whereby norms of left is actually not in a situation whereby norms of left is actually not less than or equals to mid value, let's say that the number at the left is 8 and the middle value is now telling us about 3, we see that there's no way 8 to 3 correlates, so it is definitely not sorted. I mean the left subarray is not sorted, so we want to go for the right subarray now. So and now it means that the right subarray will be sorted. So and why I say that it means that the right subarray will be sorted is because this array is rotated. So at any point in time, at any index, at any position, is either the left subarray is sorted or the right subarray is sorted. So you understand, if the left subarray is not sorted, the right will definitely be sorted. Let's consider a index 8, 9, 1, 2, 3. You know, if we place it at 1, if our midpoint falls at 1 now, if we look from the left, which is 8 to 1, we see that no, it is not sorted. Definitely 1 to 2 or 1 to 3 or 1 to 4 or to the end of the array to the right will definitely be sorted. So, and in such a situation whereby the left array subarray is not sorted but the right subarray is sorted, we want to check if the target also exists here. So if nums of mid is greater than, no, if it is less than the target, which is less than equals to, so we won't say that greater. Why? Because we're trying to check between the range of the right subarray. So, and in the right subarray, the midpoint is like the left, is like the smallest, is the least position. So if it is less than target and target is less than equals to, why am I putting equals to is because target might even be the target might actually be the very last position, which is nums of right. So we don't want to just say less than, so we won't skip that particular one. So our target is k, we collected it as k. So if in that case nums of mid is less than, that is if it is in the range of the right subarray, we want to set our left, of course, to mid plus 1 to narrow down. Otherwise we want to set, if it is not there, what we are going to do is that we are going to set our right pointer, so it is sorted fine, but the target does not exist in that subarray, then we don't need any, we don't have any matter with it, we don't have anything to discuss with it. We want to set our, we want to narrow to the left because it's going to be there. So, and then what we do is that we just return okay. So now the thing is that you see, the thing about this is that if we loop out of this this while loop, mean that they eventually met, right, without returning mid. Don't forget that we have placed a condition here whereby it will be checking if mid eventually fall at the right target. If it's return, then definitely we'll be returning -1, and that signifies that as much as we loop and as much as we we perform a binary search up to the point whereby left and right met, nothing is being returned. Mid value is not the target is not found, so we're gonna return -1. So is either along in the loop, along in the iteration, it returns mid, or it loop out of the iteration and return -1. So well, this time around I it skipped my mind to put in the parameters I'll be needing, so let me go check it out now. Alright, this is it, our norms and our targets. So we're calling the function print, so it could print this for us. Passing the norms and targets key, so we're gonna collect it as key, fine. So let's call this function now and let's see how it goes. Alright, we have two printed, so I think this is some sort of flawless. So we have the right answer printed. If we look at it, this index 0, index 1, and the value target 1 is found at index 2, which is correct. So that's how we solve this problem, just logically and interestingly. I hope you understand this. Don't forget to like, to comment, to share. Please don't forget to do that, and also subscribe to this channel. Thank you.